So this is going to be focused on one couple of aspects of SIDM. One in particular, I want to motivate sort of the recent work that um, are telling us that for viable models, if you want to make changes uh, to the way galaxies evolve, then the cross sections for SIDM have to be large. So that's my main job in this talk. Okay, so I'll start out with some sort of brief motivations for SIDM, but you guys have probably all heard about this anyway. And then the key thing is to like sort of motivate these large cross sections. And I'll end with a couple of thoughts about like, testing these large cross section models. In the morning, we heard about stellar streams. I'll just touch upon satellite densities and these perturbers that Simon was talking about. Okay, so at the back of your mind, thinking about like sort of the particle models for it, SIDM is an example or is a corner of a broader way of thinking about dark matter and sort of these dark sector models, where you basically, the answer to why we haven't seen the dark matter or detected it is that it's very weakly coupled to the standard model. It's off on its own sector. And immediately when you draw something like this, you realize that there's no reason anymore for the dark matter or anything in the dark sector to be at very high mass scales. And so in that sense, like with the low mass scales, self-interactions become something very generic that you want to test for. There's also like, it gives you new mechanisms for creating the dark matter, right? So we know it exists, and therefore you need to be able to create it somehow in the early universe. And then if you really want to impact like structure formation in galaxies, then it's very easy to like, do a back of the envelope calculation, and that'll tell you that, you sort of want self-interaction cross sections, so these elastic cross sections over mass to be something of the order of a barn per GeV or larger, right? That's sort of the place where you want to be. Let me skip through this. This is a very large parameter space. As you can imagine, there's lots of things you can put into the dark sector. And there are many ways to proceed. So for example, a lot of people will focus on looking at sets of parameters that actually allow you to create dark matter in a well-defined way with the right relic density, and then focus on those things. I'm going to look at a slightly different lamppost. I'm just going to ask, like, when there are models that can actually change galaxies in an observable ways, and in particular, I'll focus on this idea of like increasing the scatter in the central densities of field and satellite galaxy halos. In this case, for this part of parameter space, what are the observable consequences? Okay. In order to like actually make this work, you will need a velocity-dependent cross-section. So for those of you who haven't thought about this at all, I find it very useful to just think about a standard model example to know that having cross-sections of order like 20 barns is not something weird, like it exists in the standard model. So here's an example of just a neutron-proton elastic scattering cross-section. That's the famous 20 barn number. And it changes with the kinetic energy, or you can think of it, this axis as the relative velocity of the particles interacting. So for example, if I wanted to put some relevant numbers here, this would be the bullet cluster region. And if I'm thinking about rotation curves in galaxies, it would be that region, right? So it's not hard to imagine writing down models. You don't have to even cook up new things. You can think about the standard model and sort of like go off it where the velocity dependence comes in, right? So the key thing is like if you want velocity dependence, you need two mass scales in the problem. The simplest things could be the mass of the dark matter, and then there's a mediator, like Oren was talking about in the morning. But you can have more other things like atomic dark matter, for example, where you have a lighter fermion, the analog of the electron. Okay, so velocity dependence, easy to write down, and that's what you're going to need. So just keep this at the back of your mind. There's a cross-section versus velocity, and it's going to be high at small velocities, and it's going to fall at large velocities. Okay, here's an example of something, and I don't want, and I'm not going to focus on this. I'm just giving you an example of like something done with a certain simplified model by Camila Correa. These are these gravothermal models, and the idea is that eventually when we get to do this with enough data, you'll be able to map something like this out. And so here's like cross section over mass. The number is about 100 centimeters square per gram, right? So roughly a centimeter square per gram is the same as a Bahn per GeV, right? And then it falls with relative velocities. You have a lot of constraints on the cluster scales. The best constraints don't come from the bullet cluster. You shouldn't really bother with it as far as SIDM constraints are concerned. It really comes from the cores, looking at the cores of clusters through lensing. And that puts you somewhere in the ballpark of 0.1, 0.2 centimeters square per gram. Okay. And so you really do need this velocity dependence. There's no getting away from it. Either you have CDM, which is lying sort of down here, or you have some velocity dependence like this. So I'm going to spend the rest of my talk really motivating why you need to be up there. So the first thing about is I'm going to look at the diversity of like field galaxies. And this has been around for quite some time now. And the general idea is really very simple. It's to basically look at, so this is data for some 4 different galaxies. The key thing in this plot is that they all sort of asymptote out to the similar Vmaxes, so like flat part of the rotation curve, like around 80 kilometers per second. But you can see that they all rise very differently, okay, in the inner parts. And that rise is just really telling you about the dynamical mass that's there in the center. And for example, if you measure the slope of this thing, it's going to give you the density of the dark matter that's in the center. And so it's it's clear that as you go, things are denser here. That's why the rotation curve rises faster than there. And the question just is why? Okay, why are there? Why does this happen? And in particular, this is really just telling in this case here that you have big cores, and so there has to be a mechanism for creating these cores. Okay, and these sets of galaxies have been around for a while, and many people have noted this is just a paper I like that I wrote back in 2010, and it's essentially the same story, but put in different variables, and I'm going to use these variables for most of the talk. On the x-axis is Vmax, so let's just think of it. It's not exactly the same thing, but just think of the flat part of the rotation curve. Okay, so it's you can focus around 80. And there's a bunch of low surface brightness galaxies here, 7 of them. And what's plotted here is essentially the core density you would get from fitting to them. Don't worry about the symbols. The box gives you a sense of the systematic errors here. And essentially, you have around 80 kilometers per second, so maybe like 70 to 100. You can see this huge spread, right? This is just 7 galaxies. But you can already see that there's a large spread here that's more than an order of magnitude in the core density. Okay, and if you're living out here, you'll say, this is a big, this is a system like this with a big core. If you're out there, you're not going to distinguish it from a cusp. Okay, and so that's one way to frame the diversity of these field galaxies. But the diversity is, what happens in the dark matter probably is also reflected in the stars. So here's a compilation from Stefan Corto and collaborations. This is the probes 1 data set, and this is from the paper by Frost et al., where they're comparing it to like Nihau simulations. This S here is the same slope that I showed you before out here. Right, so they have some very simple fitting techniques for the rotation curve. It might not look like much, but remember, this is log of the slope, right? So down here, and this is the magnitude, surface brightness. And so down here, you sort of rise to 10 kilometers per second in 1 kpc. So you go out at kpc, you get to 10 kilometers per second. Whereas some of the galaxies out there, you go out to a kpc from the center, and you've risen to 100 kilometers per second, right? So this may not look like much, but this is like a huge diversity out here, right, in terms of the rotation curves. And that same thing exists, for example, if I look in, at fixed S, there's a large range in the stellar densities. Okay, so this is a proxy for the stellar density, I think at 1 kpc. That's why they have the 1, I forgot. And so this is happening both in high surface brightness, well, relatively high surface brightness, but low surface brightness galaxies too, right? So there's a range of stellar densities in these systems, and the dark matter is distributed in very different ways. And so this is what I would say is the right way to think about diversity. Is not to look at like any one thing. Am I getting a core or a cusp? It's sort of almost irrelevant at this point. You want to be asking, how is it correlated with the stellar distributions? So I'm going to boil down the solutions to this kind. People have been talking about it for a while into 3 things. It's a really simplified view. But one is simply that these are rotation curves. And your interpretation of the data is wrong. We can talk a lot more about this. And there's no such thing as code halos, right? It's all just an artifact that you don't understand the data really well. And there's been a lot of papers written on this, and a lot of work being done now in terms of taking a hydrosim and then sort of making observables that are the rotation velocities out of it, and trying to get at this. And we can talk more about it in the discussion if you want. Another thing is, and I'll just briefly touch upon this, is like what happens when you have really strong feedback in some of those plots. And then the third thing is SIDM. Okay. All right. So very quickly, for example, this is from the Nihao simulation, right? And so if you have let's look at this plot. This plot is just talking about, again, this is like the Vmax, and then this is the velocity measured at 2 kpc. Okay, so it's just giving you a sense of the inner density of the dark matter. And again, this plot you want to interpret carefully because most of the diversity was like for galaxies sort of out here, and you can see this range here. And so when you have feedback, in this case, very strong feedback, you're very effective in driving both the stars and the dark matter out and actually creating cores. But that's also the problem in some systems where you're not able to form compact enough stellar systems and high enough dark matter densities, right? So these things can be constrained, right? This is not to say that the Nihao level is the right level. Maybe there's some other level of feedback that'll come out right, but there is actually data here, and it's multidimensional data. And so I'm not that pessimistic that down the road, we will be able to constrain these things. Okay, so let me just, let's look at SIDM. And this is just a simulation, just a advertisement to a work that's going to come out soon, where we're running a bunch of fire initial conditions with very high cross-section. And the interesting thing is nothing bizarre really happens, even though the cross-section is 70 centimeters square per gram. So this is still a DMO. We will be running hydro soon. I guess one thing you can kind of see is that things do get a little bit more spherical as expected. If you have 70 centimeters square per gram, a big chunk of the halo is thermalized and it gets spherical. Okay. And in low surface brightness systems, that might be one signal, which is that CDM systems are probably going to be way more triaxial than SIDM with these kinds of cross sections. Okay. And here is the same galaxy, and now you can see what's happening to the density profile. Now the outer part's more or less set. You have this big core. And as time goes on, you can see that the core density starts rising. So this is, again, repeating it now. So you can wait until right about now, the outer parts are sort of set. You have a big core that's going to be roughly half of the NFW scale radius. And at this point, he's transferring from outside in, and you form that. You start getting into that gravithermal collapse phase. So if I just track the central density over time, you can see a characteristic shape. And that looks something like this. And so this is a plot of the central density normalized to what you would sort of this rho S, which you can just fit an NFW to the outer parts and extract that. So that's sort of the NFW scale density. And that's plotted here with respect to time in some units, and that I'll describe in just a bit. And this is not from an n-body simulation. This is from a gravothermal code, like the one that Oren was talking about. And you start out sort of with an NFW-ish initial condition. You start forming a core. And then you spend quite a bit of time in this phase here where you have sort of the minimum density. And that's about something like 2 times rho S. Okay? And that's really the thing that's been investigated the most using simulations and analytic models in the literature, right? That's the place where even if you change the cross-section by factors of few, nothing much happens. It's very predictive. It's a very stable solution. Okay? And the reason for that goes back to this time scale. This time scale depends on 3 things. One is sort of this characteristic density, rho C0. You can just replace that by rho S. So that's just the NFW scale density. VC0, just replace that by V max. Okay, so the maximum rotation speed that you get. And then there's a funny looking average of the cross section. The reasons why it actually works this way is not very well understood from first principles, but it seems to do a good job for a very large range of models. Okay, and so essentially, like if the cross section is small enough, then most of your galaxies will lie here. And even if I were to change the cross section, let's say by a factor of 2, you'll just move a little bit there. This is a huge range in time. Okay, so that's why it was easy to construct solutions, like analytic solutions in this part. They are very close to it's a quasi-equilibrium solution, and there's excellent analytic models. In fact, it actually does a really great job of fitting to full hydrosims. Okay, so it's a very predictive model space. And eventually, I think it's just ruled out. Right? You just can't live here. It cores too much, just like Oren was talking about in the morning. Okay. But I do want to emphasize that because it's this is not something you can do in CDM because you don't have the same drive to equilibrium there. Here, you can just solve one differential equation, essentially, and get the density profiles of real galaxies, which is kind of amazing. And those are these solutions here. So even though I'm going to say that part doesn't work in detail, most of the solutions that you see here will carry over into the part that I think, at least for now, works. Right? So here are results for density profiles, and this is just analytic. Okay, it's just literally just solving one differential equation for about 130 galaxies. The cross section's fixed to 3, but it doesn't matter whether it's 3 or 5 or 10. The results don't really change because I just showed you that you're at the sort of the bottom of that density versus time plot, and it does a pretty good job. Okay, of fitting these curves. The colors here are just giving you a sense of the surface brightness of the galaxy. So the more orangish it is, the lower the surface brightness. The redder or the more violet it is, the higher the surface brightness. So you can sort of also see an ordering that when the rotation curves rise slowly, they also have low surface brightness. It's not a perfect ordering, as I will say in the next slide, but it's a really good, does a really, really good job of fitting it. Right? And so you might ask, well, how do you actually get the diversity? And I don't have time to go into it, but essentially it comes from 2 places. One is just the natural assembly history, so the halo concentration. The other one is the stellar distribution, right? So in making these solutions, I have assumed that the stellar distribution is as observed, right? And that has an impact on the SIDM solution. Okay. Okay. So why doesn't it actually work? Well, this is a compilation, and it looks good when you put 135 galaxies together. But what if you just pick out the galaxies that are the lowest surface brightness? Okay. And so that's what I've done. This work just came out recently. That's what we did in this paper. Some of these are from the same sample that you saw in the previous, but some of them are newer observations. And don't worry about the lines going through, but you can see the data. And really what I want to highlight is that they are all very low surface brightness galaxies. To zeroth order, dynamically, in terms of the rotation curve, you can forget about the baryons in fitting this. And you can see that the data, there are some examples where the rotation curve rises really fast. Look at this one. Within a KPC, it's gotten up to 80. Okay? And then there are some others that rise more slowly. So it's a large mix of it. If you were to put it into that plot I showed you before of the core density versus Vmax, it's the same thing. Around 70 to 100, you see this this is now log of the core density. So this is a little more than an order of magnitude spread here. Okay, so there are things that have cores, but then there are things that have that can be fit with cusp. We have very small core sizes. They're very dense. Okay, and that's just another way of saying that there is this diversity in these low surface brightness galaxies. And in particular, there are these things up at the end that rise pretty quickly, and so they're really dense systems, right? And so you can sort of get a sense of how are these being fit in these SIDM models that just make cores, right? And I'll show you on the next slide what's happening. And this was sort of highlighted by Santos et al. A few years ago. So how are we fitting these galaxies when we had 3 centimeters square per gram? Essentially, what was happening was the concentration was being picked to be very high. Okay, so normally you would expect things to be within sort of plus and minus 0.2, 0.3 dex. Okay, and a lot of them were out here, and so the way the solution was working was that it was basically trying to jack up the concentration and get the densities up. But while this is not I would say, maybe this is, maybe there's some systematics here, and you can avoid, maybe some of these, there's some issues with the data. But to me, it just looks funky to have so many of these systems sitting out here at 0.3 dex. Right? Why would these low surface brightness galaxies be sort of these very early forming, very dense systems? Right? So unless there's actual evidence for this in some other way, it just seems this is not really the right solution. And so what else can you do? And that gets me to, there's only 2 minutes left. Okay, so that gets me to this part, which is that you could live on that part, and now your diversity is really enhanced because if you're living on this part, it's very sensitive to, for example, what your rho c is. Your rho c0, which is essentially the concentration of the halo. Vmax gives you some idea of the mass of the halo, right? And so if there was a solution here, there's another solution probably sitting out there. They have similar densities, okay? And so it's just a question of asking, does it really work, this thing? And it does a phenomenal job, right? So you can just fit these things with something like 40 centimeters square per gram. The concentrations are median. You don't have to do much. So you basically get all of the good things that we saw with the moderate cross sections. But now you have a lot more diversity built in because things can sort of be out here. And with very small changes in concentration, you can get very different densities, right? So the diversity is, in that sense, enhanced. So I'll just show you one slide with the Milky Way, but sort of Oren already said this. And how do these, now you can ask, well, these things work maybe for field galaxies. How do you test them with Milky Way satellites? And the moderate cross sections do really badly for Milky Way satellites. So Oren already mentioned this, that this is the moderate cross sections lie here. They just score too much. And just the power of these simple analytic things that you can, Oren has been doing, I want to show you a simulation. And basically, this is an n-body simulation. Here's some of the Milky Way data. So this is V versus R. And most of these curves are from these n-body simulations. And what you can clearly see is that the data is just lying out there on the top, right? So maybe one or two can be sitting out here, but as an as an ensemble, the data, the model scatters below the data, right? And so that's the sense in which that's the sense you're capturing in this isothermal coring region, right? So moderate cross sections just don't work, and so what you really want is to be living in that region out there, where the cross section is high. So the field galaxies, this is a bit like, these are not theorems, but it seems like from looking at the densities that the field galaxies and the satellites are both telling you that you need to live at the high cross section regime. Just one quick thing is that the diversity for these in the subhalos, you have the concentration, but now you also have other things. And Oren mentioned this. You have tidal mass loss and dark ram pressure stripping that can give you like really different density profiles in the Milky Way. Okay, let me show you one slide, and then we'll end. And so this is a simulation. This is a DMO run by Danning Yang, Ethan Nadler, and Haibo Yu. And essentially, it's a simulation that has Milky Way-like systems in here. And I want to show you this plot here, which is just a Vmax, Rmax. This on the left is CDM, and on the right is SIDM with pretty large cross-section, like somewhere around 100 at small velocities. And what I'll draw your attention to is that they sort of are in the same ballpark, right? But what you see in SIDM is a lot of scatter to high Rmax. So these are really puffy systems. It's surprising that they survive. Maybe they've fallen recently. And things out here, right, that are really dense. So at the same Vmax of 30, your Rmax is down by like almost an order of magnitude, right? These things have core collapsed in these simulations, right? So essentially, it's like CDM with wings, right? You get very, very high density and very low density. Not all of them, right? Only a few will core collapse, but they do core collapse. And then some of them get really less dense because they're still sitting on that part of that curve density versus time where you haven't risen up. So I think the opportunity, and maybe we can just put this in the discussion section. The opportunity that we have is to like think about, are there ways of detecting these things that are denser than CDM? Okay, so it says 0, so I'm going to go to the conclusion. Okay, so hopefully I at least convince you about this part that some of these models in SIDM parameter space are extremely predictive, and that's just because there's many ways to be not in equilibrium, but there's one way to be in equilibrium, and so the predictivity just comes from that. There are large portions of this model space that are already ruled out. Okay, this is really wordy, but what it's saying is like if you want to be in the viable region, I think you have to be sort of at low velocities up at the 50, 100 centimeters square per gram level. And then the cross-section has to just fall. And that's really interesting because that's just saying that there's something in the dark sector that's lighter than the dark matter itself, maybe at the MeV scales. And searching for these subhalos and satellites with central densities higher than predicted in CDM, I feel that's like the exciting thing. All right, thanks.
We have time for maybe one quick question. Yeah.
Wouldn't you radiate this lighter object?
Yeah. So in much of the parameter space, that just turns out to be, unless you get to very high densities, it doesn't happen. So we have a paper coming out where we look at, the gravothermal collapse is happening, and the typical thought is that the core will get to relativistic energies, and then there will be relativistic instability and you form a black hole. But at some point, it'll get to a point where you'll have the Bremsstrahlung lung, and it'll start cooling. And that actually changes it. But again, depends on what the fine structure constant is and things like that. But in large parts of this parameter space, it only happens at like very, very inner regions of the core. So it's going to change what the final black hole mass is in the center of the halo, but not the evolution. But you can write down models where, of course, the dissipation is very, very large. Yeah, yeah. But not in these parts of parameter space, yeah, not.